All right, so this is the last section of Chapter 3, Section 3.11. So we'll call this Lecture 3 Part 11. And in this lecture, we'll talk about hyperbolic functions, which have quite a few engineering applications. So it's Lecture 3, Part 11. Hyperbolic functions. Okay, so what are hyperbolic functions? Well, they're basically definitions of a special class of function. We define 6 hyperbolic functions. So let me pull it up from the lecture notes so I won't have to write all 6 definitions. One second, almost done. All right, so let me paste this in here. So here we have the definitions of hyperbolic functions. So, for instance, the hyperbolic sine, written as S-I-N-H and pronounced sinh. So the hyperbolic sine of h, or sinh x, is defined according to this formula. It's the exponential of x minus the exponential of minus x divided by 2. So this is a definition. All right, the sinh of x. And then we have the hyperbolic cosine of x, often read cosh of x, and it's e to the x plus e to the minus x over 2. And then we have the hyperbolic tangent of x, often pronounced tang of x. Okay, this is, of course, sinh x over cosh x, which is e to the x minus e to the minus x over e to the x plus e to the minus x. And then the other 3 are, like, for instance, the hyperbolic cosecant of x, the hyperbolic cosecant of x, sheesh of x is 1 over sinh of x, which of course is equal to 2 divided by e to the x minus e to the minus x. Okay, and then we have the hyperbolic secant of x, sech of x. Okay, and that's 1 over cosh of x, and that is 2 divided by e to the x plus e to the minus x. And then we have the hyperbolic cotangent of x, the coth of x, and that's just cosh x over sinh of x. So as you might expect, we have graphs. We can graph these functions. So let me pull up the graphing calculator, see if we can do it with the tool. I meant to put this on a different page. So y is equal to sinh of x. Okay, and that's shown in red, right? So it looks almost like a tangent function in a way, but remember the definition. If we use the definition, if we use the definition, we know that the hyperbolic sinh function, or the hyperbolic sine function, that is defined as y is equal to e to the x minus e to the minus x over 2. So it's actually the difference of two exponential functions. And so if we were to graph each of the functions separately, you can see how they culminate into the definition, or culminate into the graph of the hyperbolic sine function. So let's give that a try. So for instance, let's graph y is equal to e to the x over 2. Okay, and this will be shown in blue, as you can see. And this function, e to the x over 2, forms an asymptote for the positive portion of the hyperbolic sine function. So you can see how the red curve is asymptotic to the blue curve. And then, of course, the next function, let's see, make sure I got that right. Y is equal to negative 1/2 e to the minus x. So let's graph that. That will form the negative asymptote. So y is equal to negative e to the x divided by 2. Okay? Not okay, so this would be shown in green. All right, and so turns out, is that right? Y equals to, oh, that should be minus x. I beg your pardon. I got the sign wrong on the exponent. They look kind of weird. Minus x. Okay, so we'll go with that. Okay, that should be better. Okay, so now, pan. So you can see that the sum of the blue curve and the red curve, when we sum the blue curve and the red curves together, we'll get the hyperbolic sine function. Okay, you see how that works? And the green curve is actually kind of an asymptote for the negative portion of the hype sine function. So we can, from here we can say, okay, the domain of the hype sine function, hyperbolic sine function, I'll call it hype sine as another word for it, is the set of real numbers. And the range of the hype sine function is the set of real numbers as well. So it's a nice function. It's an increasing function, and has no local mins nor local maxes. It does have an inflection point at the origin. In other words, the concavity switches at the origin for this function. And what else can we say about this function? Okay, so that should be good enough for now. Later on, of course, we'll take its derivative and we'll calculate its inverse, and we'll reformulate the hype sine function in terms of the natural log. But let's do the other 5 functions next, and then we'll move on to those details. All right, so let's talk about, okay, so I'll get rid of this. Let's talk about the hype cosine function, or the cosh or hyperbolic cosine function. So let's get rid of all these. And so I will go y is equal to cosh, hyperbolic cosine of x. And that will be shown in blue. Now, look at this curve. Hyperbolic cosine is always greater than 0 on its outputs. Its domain is the entire x-axis, but look at its range. The range of the hyperbolic cosine is this interval. Y is always greater than or equal to 1. Okay, so here's the range. And then so we have a restricted range for the hyperbolic cosine x. Now, and we know that the definition of hyperbolic cosine function is the sum of two exponential functions. The sum of two exponential functions. And we can see how this the sum of these two functions produces the purple curve. So let's try that. All right, so let's graph an overlay graph of, say, y is equal to e to the x divided by 2, and that's shown in orange. Okay, and then the second function, which when summed to the orange curve, is y is equal to e to the minus x divided by 2, and that's shown in black. Let's divide it by 2. Make that divided by 2. Okay, there we go. All right, so let's take a look and see what we have here. So if we were to sum the orange and the black curves together, we'll get the purple curve. Okay, so for instance, right here, the orange and the black curves intersect at the point 0, 0, and 0.5. So if we sum 0.5 plus 0.5, we'll get the vertex of the hyperbolic cosine function, which is, I don't know how to make this go away. Okay, yeah, 0, 1. Okay, so there's the hyperbolic cosine function, rather peculiar function. Okay, so the next function we can talk about, say, is the hyperbolic tangent function. So let's explore its graph. So y is equal to hyperbolic tan of x. Okay, and this will be shown in red. All right, and if you notice, it looks almost like the graph of the inverse tangent function. Okay, with the exception, of course, oops, I just erased it. Y is equal, try it again. Y is equal to tan x, hyperbolic tan x. Shown in red now. Okay. So let's look at the properties. So again, the domain of the hyperbolic tan function is shown in red is the set of real numbers. So we can put any real number into the function and get an output. But now the range, okay, so like I said, the hyperbolic tangent function looks almost like the inverse tan function, with the exception is that the asymptotes are not pi halves and negative pi halves, but in this case they're 1 and negative 1. So it has asymptotes at 1, negative 1. Okay, you see the asymptotic behavior of the hyperbolic tan function. And of course, again, to reiterate the definition, y is equal to hype tan x, which is equal to e to the x minus e to the minus x divided by e to the x plus e to the minus x. Right? So this is the graph of the hyperbolic tan function, and now we know its properties. So that means clearly the hyperbolic tangent function is an increasing function. It has an inflection point at the origin. It changes from concave up to concave down at the origin, and so it's everywhere differentiable. So, and we'll explore those properties shortly. So the next function we can talk about then would be, say, the hyperbolic secant function. Okay, so let's explore the graph of the hyperbolic secant function. So y is equal to hyperbolic secant of x, and that's shown in purple. Okay. And it looks almost like a normal distribution, a bell-shaped curve, but it's always concave down. Okay. It attains a global/local max at 0, 1, okay, right here. And it's asymptotic with the x-axis. Okay, so a rather interesting curve. The other two, hyperbolic cotangent, the hyperbolic cosecant functions, their graphs, I'll let you do on your own to explore the properties. Okay, so let's see here, some things that we can do with hyperbolic functions. Next page. So we can actually, say, solve some physical problems that are big in, say, a vocation like civil engineering. So a formula that's used quite often, let me paste it in here for you. Bear with me while I cut and paste here. So for instance, in ocean engineering, or in physics, oceanography, this formula crops up a lot. The velocity of a water wave with length L moving across a body of water with depth D. So like in the wintertime, if you go to the North Beach, Oahu, okay, and you want to know how fast the big one's coming in. Well, you can estimate the depth of the bay, and then you can get an estimate of the length of the water wave, and then you can get its velocity. Okay, and it'll be used according to this formula. You use the hyperbolic tangent function to calculate the velocity of an incoming wave. And I'd be curious to know if the lifeguards would know this to chase novices away from surfing on the big waves on the North Beach. Somebody let me know. Okay, well anyway, so there is some utility to knowing hyperbolic functions. So if you notice that the hyperbolic functions kind of are written like trig functions, right? Trigonometric functions, except they have that little h in the name of the function. So nevertheless, what that means is that we have identities. We can prove identities of the hyperbolic trig functions. So let me pull up something here. So some identities we might want to consider would be like showing that the hyperbolic sine function is an odd function. And you can just deduce that from the graph. But if you want to prove it more rigorously, just use the definition. So we can say, let's prove that the hyperbolic sine function is an odd function. So what is the hyperbolic sine of negative x? Well, we know the hyperbolic sine of x is equal to e to the x plus e to the, no, I'm sorry, minus e to the minus x, sorry. Minus e to the minus x over 2. So what is the hyperbolic sine of minus x? So sinh of minus x, that would equal to e to the minus x minus e to the x over 2, which is equal to the minus sinh of x. So that was a sinh to prove. Okay. So how about we prove the sinh of a sum? Use this right here. Let's work this one. Okay, the sinh of a sum. All right, so there's a little bit of a trick to doing this, and I'll show you. So sinh of a sum. The trick to proving this identity is to start on the right-hand side, okay, and then collapse it into the left-hand side. So start with the right-hand side. So the sinh of x times the cosh of y is equal to, use the definitions, that would be e to the x minus e to the minus x over 2 times the cosh of y, which is e to the y plus e to the minus y over 2. Okay, so let's do the multiplication. So that would be I'll use FOIL for the numerator. That'll be e to the x plus y plus e to the x minus y minus e to the minus x plus y minus e to the minus x minus y over 4. Okay? And then let's do the cosh of x times the sinh of y. So what is that product equal to? So the cosh of x times the sinh of y. Okay, so that would equal to e to the x plus e to the minus x over 2 times e to the y minus e to the minus y over 2. So we'll do the multiplication, so that would equal to e to the x plus y minus e to the x minus y plus e to the minus x plus y minus e to the minus x minus y. All of that over 4. All right, and so now all we do next is we just take these two terms and let's add them, okay? So we plus those two terms. So the screen is kind of scrolling, so let me extend the page. So we have sinh x cosh y plus cosh x sinh y. That would equal to, okay, so let's see, how do I copy and paste? Where's my select? Edit, select. Yeah, select, right? If I do this, copy, so I'll paste here, and then I'll go plus, and then I need to copy this piece. Pretty cool, huh? Copy, and then paste here. And so let me touch it up a little bit. Let me erase this. Erase this, okay. And so we want to add these two quantities together. All right, so what do we have? We have so we can add the numerator, so that would be 2 times e to the x plus y. Okay, let's see, this term will cancel, and this term will cancel, and then we're left with minus 2 times e to the minus x minus y over 4. Okay, and then we can cancel the 2, so we're left with e to the x plus y minus e to the x minus y over 2, which is equal to the sinh of x plus y. Sorry, that should be a minus right there. Okay, the sinh of x plus y. Right? So we proved a hyperbolic identity. Right? Easy enough. Okay, so I'm going to leave it to you to prove the cosh of a sum. Okay, so I'll leave it to you to prove the cosh of a sum. And you see how they kind of mimic the trigonometric identities? In a way they do. So how about, except for this one, how about we prove this identity? The cosh squared minus sinh squared is equal to 1. So I'll do that on the next page. So we want to prove cosh squared x minus sinh squared x is equal to 1. Okay, so replace cosh squared with its definition, so that would be e to the x plus e to the minus x over 2, square it, minus the sinh squared, that would be e to the x minus e to the minus x over 2, quantity squared, and that's equal to 1. Okay, so we complete the squares using FOIL. So we'll have e to the 2x plus 2 plus e to the minus 2x over 4 minus e to the 2x minus 2 plus e to the minus 2x over 4 Okay, so completing the square, and what does that equal to? So that would equal to 2 e to the 2x plus 4. No, I'm sorry, I beg your pardon, that's not right. We have a cancellation here, it looks like. We've got a couple of terms canceling. Let's see, so if we don't add, we subtract them, I believe. So this term will cancel, and this term will cancel in the subtraction, because we're doing a subtraction. So 2 minus 2 is 4, so that would equal to 4 over 4, which is equal to 1. Yeah, so we're good. Okay, so we got that. All right, so and I'll leave it to you to prove the other identity, 1 minus hyperbolic tangent squared x is equal to hyperbolic secant squared. And again, you just resort to using the definitions of these functions to prove it. Okay, so hyperbolic identities. All right, so what's next in this topic? All right, so we can take derivatives of the hyperbolic functions. So let's try that. I think I may have a technical note somewhere here. Let me see. Bear with me, I'm pulling up another technical note from a different source. Let me find the page that I want to go to. Somehow, okay. So let's see. Oh, yeah, it's not there yet. We're not there yet. Okay, so let's go ahead and calculate the derivatives of the hyperbolic functions. And I think you should be able to do these yourself. So consider finding the derivative of the hyperbolic sine function. The derivative with respect to x of hyperbolic sine or sinh x. Okay, so this would just be again, you just replace the hyp sine with its definition. So that would be e to the x minus e to the minus x over 2. And then you just take the derivative of a difference of two functions, and so that would equal to e to the x plus e to the minus x over 2. And of course, that's just equal to cosh x. All right, simple enough. So you should be able to find the derivative with respect to x of cosh x. And that, of course, I'll expect you to be able to prove that the derivative of the cosh function is just a sinh function. So it's a little bit different from trigonometry. So you do that on your own. And let's see, maybe I can do one. How about we take, I'll help you with this one. So we calculate the derivative with respect to x of the hyperbolic secant function, cosecant function. How about CSC, hyperbolic cosecant of x? Okay, so replace hyperbolic cosecant with its definition. So that would be 1 over hyperbolic sine, which is 2 over e to the x minus e to the minus x. And then we use the quotient rule for differentiation. So that would be the bottom function times the derivative with respect to the top. The derivative of the top with respect to x, excuse me. Got tongue-tied there. Yeah. Okay, so that would be 0 minus 2 times the derivative of the bottom function. So that would be e to the x plus e to the minus x divided by the bottom function squared. So that would be e to the x minus e to the minus x squared. Okay, and so we're left with, that's a minus right there. So we have minus 2 times e to the x plus e to the minus x. Okay, and I'll go ahead and write the denominator as a product of terms. So that would be e to the x minus e to the minus x, okay, times e to the x minus e to the minus x. Okay, so I just went ahead and expanded the square as a product of factors. And the reason why I did that is because now we have a pattern. Because you may recognize that this factor right here, that's hyperbolic cotangent. Okay? And this factor that I'll accentuate in blue, that's hyperbolic cosecant. All right, so we're left with the negative of sheesh of x, hyperbolic cosecant of x, times the coth of x. All right, so that's pretty straightforward. And that follows from trigonometry, the definition of the cosecant function. The derivative of the cosecant function, that is. Okay, so I'll let you do the derivative of the hyperbolic secant function. Okay, so how about we do the derivative of the hyperbolic tangent function? Okay, so we want to calculate the derivative with respect to x of hyperbolic tangent x, so that would be the derivative with respect to x of e to the x minus e to the minus x over e to the x plus e to the minus x. So we'll have to use the quotient rule for differentiation. Okay, so that would be the bottom function times the derivative with respect to x of the top, so that would be e to the x plus e to the minus x, minus the top function, which is e to the x minus e to the minus x, times the derivative of the bottom function with respect to x, so that would be e to the x minus e to the minus x, okay, all over the bottom function squared. So that would be e to the x plus e to the minus x, quantity squared. Right. So now we can simplify the numerator. So that would be e to the 2x plus 2 plus e to the minus 2x. I just did a FOIL. Minus, okay, so we have e to the 2x minus 2 plus e to the minus 2x. Okay, all over e to the x plus e to the minus x, quantity squared. Okay, and so that would equal to, well, let's see, we have some cancellations going on. This term cancels, and so we're left with 4 over e to the x plus e to the minus x squared, and that, of course, is equal to the hyperbolic secant function squared. That's not 2x, that's a square. Okay, so the derivatives of the hyperbolic functions that I didn't do, I have an expectation that you can do. All right, so the next topic we'll talk about will be the inverse hyperbolic functions. Okay, so remember the graphs. Okay, so let's see here. What's the best way of depicting this? Let me check something. All right, so let's talk about, say, like the inverse hyperbolic sine function. So I have a technical note here that I'll paste in the whiteboard. Hang on one second. Let's see here. So we'll talk about the inverse hyperbolic sine function. And we'll even go as far as calculating its derivative. So here's something that I have typed up. And this note is on the class website. All right. So the inverse hyperbolic sine function. All right, so it's defined, here's the notation, sinh inverse x, and it's defined if and only if the sinh of y is equal to x. And y is in the set of real numbers, and x is in the set of real numbers. Okay, so since the hyperbolic sine function is 1-to-1, it's a 1-to-1 function as we saw from the graph, then that means it does have an inverse, and the inverse is this function right here, the inverse hyperbolic sine function. So I guess we can explore its graph. So let's see what the inverse hyperbolic sine function, the graph of which looks like. So it should be basically you just reverse the domain in the range of the hyperbolic sine function. So it's nothing really too profound with this. Y is equal to, oops, sorry, I need to get the pointer tool. Y is equal to, what would it be? A sinh x? I'm not sure how you would represent it in the calculator. Maybe there's a help tool. Let's see, functions, check the functions. It doesn't look like this calculator treats the inverse hyperbolic secant function. The graph of the inverse hyperbolic secant. God. I'm not seeing it. Is there an inverse? Sinh. Oh well, I have to go somewhere else. Perhaps the class website. So I know your textbook has a graph of it. So let's go to calculus/m200.php. Okay. We're there. Okay. And let's see here. May have to Google for the graph of the. I don't know if these tools support it. Okay, so here's the graphing calculator. So the numerator will be a sinh x. I assume that would be it. 1. Okay, so we'll delete that. We'll make this 1. And let's see if it recognizes it. Yeah, so it does recognize it. Cool. All right, so the Wolfram calculator recognizes it. So here's the graph of the inverse hyperbolic secant function. So there's really nothing too profound about it. Not a whole lot to say about it. But what's interesting is we can reformulate the inverse hyperbolic secant function in terms of the natural log function, and here's the formula. And here's the process of how to do that. What we do, okay, is we start off with the definition of the hyperbolic sine function, and then we apply the techniques for finding the inverse of any function, okay? Okay, so what's going on here? Okay, yeah. So they solve for y. Okay, so 2y is equal to e to the x minus 1 over e to the x in this step right here. Okay, solve for y. And then what we do is we did like we did in algebra when we solved when we solve equations that contain functions. So like for instance, if we replace e to the x, if we let e to the x equal to z. Now, of course, z is always greater than 0. I'm looking at this piece right here. Z is always greater than 0 because we know if we let e to the x equal z, z is always greater than 0 because we know e to the x never falls below the x-axis. E to the x always returns a positive result. So we replace e to the x with z, and we're left with this. So we have 2y is equal to z minus 1 over z. And I hope you know where this 1 over e to the x comes from. It comes from that negative exponent right there. Okay? And so now we transform this equation right here into a quadratic in z. Okay, so now we have z squared minus 2zy minus 1 is equal to 0. So right here, quadratic in z. And then we use the quadratic formula. Okay, so what we did here, fill in the details, we have z is equal to the negative of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and so in this case, b is 1. No, let's see, what is b? b is negative 2y, right? So that would be negative 2y plus or minus, no, I'm sorry, the negative of b. b is negative 2y, so the negative of b is 2y, excuse me. Sorry, I'll get it right one of these days. So the negative of b translates to 2y plus or minus, now b squared is 4y squared. Okay, and a is 1, c is negative 1, so that would be 4y squared plus 4 all over 2a over 2. And so this would equal to, okay, after simplification, y plus or minus the square root of y squared plus 1, okay, as they've shown here. Okay, so that came from the quadratic equation. And let's see here. So one of these, so we have both a positive and a negative result for the choices for z, okay? But because we know that the square root of y squared plus 1 is slightly greater than y, okay? Because the square root of y squared is the absolute value of y, which is a positive number. And if we add 1, we're just ever so slightly greater than y. So we know then that this number is less than 0. And if you need convincing, just go ahead and graph it. And you'll notice that this is never above the x-axis or the y-axis. Okay, change y to x and graph it, and you'll see that it's never above the x-axis. So this is always less than 0. It's less than 0 for all y. Okay, so that means we reject this solution. So reject, that's the reject symbol. And so we have only one choice for z, which is right here. Now, so next we just replace z with its definition, which is e to the x. All right, and then to solve for x, we just take the natural log of both sides, and so now we have x is equal to that. Okay, so that's the inverse. Okay, and then by the properties of finding the inverse, then we just we interchange x and y for the inverse. Okay. Yes. Right. That's correct. Yeah. So we just interchange x and y, and so we know that y is equal to the sinh inverse of x, which is equal to that. So here's the formula, which you don't have to memorize, but understand how to derive. We can replace sinh inverse of x with its with the representation in terms of the natural log function. Okay. All right, and then we can do the same processes for the other hyperbolic functions. I'll just go ahead and do for now. I'll just go ahead and discuss the inverse hyperbolic cosine function and the inverse hyperbolic tan function. Okay, so, and let's see what else, and then we'll do some more derivative work. We'll take the derivatives of the inverse functions, hyperbolic functions. Okay, so now, next let's talk about the inverse hyperbolic cosine function. All right. So let me pull up that technical note. And again, this is on the class website. There's a link to it. Okay, so the inverse hyperbolic cosine function. So cosh x is equal to y. Now, we saw from the graph that the hyperbolic cosine function is a many to one function. So let's go back. You remember the graph of the hyperbolic cosine function was a catenary shaped figure. In other words, it was shaped like this. It had a vertex, a minimal point at 0, 1. Okay, so it was this graph. So it's not one to one. And so what we have to do is, according to this note, we have to restrict the domain. Okay, so we know the range. So let's see, the hyperbolic cosine. So the range, what is this? Hyperbolic, oh, okay, so hyperbolic cosine function. Okay, so what we do is we only take the inverse of a certain portion of the hyperbolic cosine function. In other words, we take this part right here. Okay, so with that, so all we do is we swap the domain and range of this green branch, and we get the hyperbolic cosine, the inverse hyperbolic cosine graph will look something like that. And I'll do it more formally in just a second. Well, I guess we could do it now. So we go back to that Wolfram calculator. Where was it? Right here? Yeah. So let's do the graph of the inverse hyperbolic cosine function. And then we'll replace it with its representation in using the natural log function. Come on. Keep snapping back. Come on. Oh, jeez. All right, so let's graph a cosh, inverse hyperbolic cosine. What does that look like? All right, so the real part is shown in blue. This isn't totally correct, but the part that we're going to be working with them so far in this class, remember, we're not working with complex numbers. So let's see, maybe we can flip let's do a real value plot. Good, gives us a choice. Yeah, here we go. Good, excellent. So we have choices now. They improved the calculator. So here's the graph. Rather peculiar graph. It starts at the point 1, 0, and then it sort of goes off toward infinity in this logarithmic fashion. So here is the graph of the hyperbolic cosine function. Okay, and you have access to this resource. Okay, so what can we do next? Okay, so we've seen its graph, and we've defined I think there's some issues here. We've defined the domain of the inverse hyperbolic function is from 1 to plus infinity, and the range is from 0 to infinity. Okay, so this is the range. So domain, okay, here you go. So there's a typo right here. This should be, that should be cosh, inverse cosh x. Okay, inverse cosh x. So here's the domain, and here's the range. Okay, right here. So now we want to reformulate. So that's not what we want to show. We want to derive a logarithmic expression for the inverse hyperbolic cosine function, right? And so we do just as we did before. If y is equal to hyperbolic cosine x, we have this expression, and then so we replace e to the x with its representation in z, and so we get this quadratic equation that stems from the definition of hyperbolic cosine. Then we solve for z. Okay, we get this equation, reject the negative solution, and so z is equal to this, just like we did before, and then we solve for x. Okay, replace z with e to the x and solve for x, and we get this expression for the natural log representation of the hyperbolic cosine function. And then if we interchange x and y, then we have the expression for, this is the expression for the inverse hyperbolic cosine function in terms of the natural log function. Okay, so that's how we calculate the inverse. Just solve for x. Okay, solve for x here in terms of y, and then just interchange x and y to get the inverse. Okay, so we've seen its graph, we've seen its inverse. So the next one I want to talk about would be the inverse hyperbolic tan function. All right, so let me pull up the technical note, and I'll just talk about these three. The other three, I'll let you review on your own, or actually I might just work those as problems, but the other three you should review on your own based on the technical content of the class website, that's posted on the class website. So here is how we can define the inverse hyperbolic tan function. All right, so let me print screen, and let's see here. So the inverse hyperbolic tan function, and we want to replace its expression with in terms of natural log. Okay, so the calculations are a little bit involved with this one, but we'll go ahead and, all right, so I guess we can look at the graph first. Strange, it doesn't post back. Okay, so A tan H. Wow. It's really sensitive to touch on this. Let it settle. Let it load. Come on. Okay, so here we go. Finally got there. So inverse hyperbolic tan graph. So again, since the hyperbolic tan function is a one-to-one function, there's not going to be much to show here. it'll just basically be one branch of what appears to be a tangent function. But it's not one branch of a tangent function, but it'll look like it. All right, and so let's look at the real value plot. And so there you have it right there. Okay, so what's interesting though is to convert it into the to a logarithmic expression. All right, so we want to prove this expression that the inverse hyperbolic tan function can be formatted like this. Okay, so again, as usual, we start with our definition of the definition of the hyperbolic tan function, and then we'll solve for y. Okay, actually we'll solve for x. Solve for x in terms of y. So remember, e to the minus x is 1 over e to the x, so we expand the negative exponents. Then we replace e to the x with its representation in z, which we know to be greater than 0. So here is y in terms of a variable substitution z. And then after simplification, we have y is equal to this. Okay? And so now all we have to do is algebraically solve for z in terms of y. So here we have a quadratic in z in terms of y, and so we use the quadratic formula. So after using the quadratic formula, we'll get z is equal to this quantity. And we reject, of course, the negative quantity. So after rejecting the negative quantity, we get z is equal to this. Replace z with e to the x, and so now we solve and we have x is equal to the natural log of this, and then interchange x and y. And so we have a representation of y, of the hyperbolic tangent function in terms of the natural log function. A very interesting formula. Okay, so that's all I wanted to say. Those are some, and of course, again, these are some important identities. All right, so now we can go on and talk about the derivatives of hyperbolic functions. Okay, now that shouldn't be too bad of an undertaking. Let's see here. Seeing which problems are useful here. Okay, so yeah, so let's calculate, say, the derivative of the inverse hyperbolic cosine function. Okay, so we want to calculate the derivative with respect to x of cosh inverse of x. Okay, so it looks like we may have to potentially use some implicit differentiation here. All right, so let me pull up the technical note. Okay, so here's one way of doing it. We can make use of the conversion of the inverse hyperbolic cosine function in terms of the natural log function, and then we can just take the derivative of that natural log function. So one way of dealing with it would be something like this. Okay, so you recall the conversion of hyperbolic cosine to a representation in natural log. Okay, so here was the formula, and we just did that. Now, all we have to do is just take the derivative with respect to x to the right-hand side, and we're done. So here we go, derivative with respect to x. So remember, when you differentiate a natural log of a function, okay, remember the rule, or the hint, or the shortcut. That's just equal to the derivative of the function divided by the function. And so that's what we're going to do here. So the derivative of x plus the square root of x squared minus 1 is just this expression right here. So, you know, we've got the chain rule. Okay, so we need to calculate the derivative as an aside. of x squared, the square root of x squared plus 1. So we're going to have to use the chain rule, right? The power rule followed by the chain rule for differentiation. So this would just be 1/2 times x squared minus 1 to the negative 1/2 times the derivative of what's inside of parentheses, which is 2x. Okay, and so this will be that part right there. Okay, and then of course we divide by f of x. And what the guy did here next was he just basically did the addition in the numerator to do a simplification. And once all said and done, so how did he get this part right here? Okay, so I'll go ahead and expand that out for you. So we know now that the derivative is this, 1 plus 2x divided by 2 times the square root of x squared minus 1. Okay, all of that divided by, what was it, x, the function itself, x plus the square root of x squared minus 1. All right, so what I'm going to do is I'm going to multiply upstairs and downstairs by the by this term right here. Okay, so I can get rid of it. So we'll have 2 times the square root of x squared minus 1 plus 2x divided by 2 times the square root of x squared minus 1 times, that square root goes over there, right? Okay, times x plus the square root of x squared plus minus 1, excuse me, like so. And then of course the 2's will cancel. And let's see. Okay, and so let's see what else we get. Okay, so this would be did I miss a term? It looks like I may have missed something here. I'm checking here. Yeah, so I think that's good. Yeah, okay, so I think we're okay. So let's see, so upon further simplification, we'll have x plus the square root of x squared minus 1 divided by x times the square root of x squared minus 1 plus x squared minus 1. Okay. Okay, let me check. Okay, all right, so we have x squared, square root of x squared plus x. Okay, so far so good. X times. All right, so now can we simplify this even further? So we need to boil this down. So x times x squared minus 1 plus x squared minus 1. So how can we simplify this now? So this would be what? Trying to think how we can simplify this. Don't see an easy way. So we divide by x. Oh, okay. I see. Maybe if we did something like okay, so if we let say y x, so let's see. So this would be the square root squared. So how do we go from there to there? So this would equal to x plus the square root of x squared minus 1. And let's factor out the square root of x squared minus 1 here. Times x plus x squared minus 1. Oh, no, not that way, the other way. Sorry. Probably want to go the other way. Let's see, let's try it this way. So that would equal to x plus square root of x squared minus 1 divided by, let's factor out an x squared minus 1. So that would be x times x squared minus 1 to the negative 1/2 plus 1. That still doesn't give us what we need. I'm wondering if I made a mistake somewhere here. Let me start over. I think I made a mistake. This is a complicated thing to resolve here. So let me start over with this. Yeah. All right. So what I'll do is I'll select so let's see here. We'll go another page here. All right, so let's start with this expression right here. See how we can simplify it. Okay, so with the guide, okay, so the 2's will cancel here. Okay, and so coming down here, I'll have the square root of x squared. Not big enough. Try it again. So I'll have the square root of x squared minus 1 plus x. Okay, so all of that over the square root of x squared minus 1. So that's the numerator, and then we don't touch the denominator. Oh, I see now. I see how it works. Okay, I got it now. Yeah, it was too obvious. I see how it works. Sorry, guys. Okay. Okay, so this is just equal to x squared minus 1 plus x. It's too simple. That was the problem. Divided by x squared minus 1. And if I do this, I multiply by the denominator, 1 over the, which is this. Okay, so like so. And then in this multiplication, those two terms will cancel out, and then you're left with this result. Okay, so there you go. So there's the derivative of the inverse hyperbolic cosine function. Yeah. All right, so how about we prove the derivative of the inverse hyperbolic cosecant function using implicit differentiation? Okay, so perhaps a simpler approach. Implicit differentiation might offer some utility here. So let's say we want to calculate the derivative with respect to x of the inverse hyperbolic cosecant function. Right? So what does that equal to? So we let y equal to and I have my inverse drawn wrong. Sorry. Inverse hyperbolic cosecant. Like so. Okay. So we let y is equal to inverse hyperbolic cosecant of x, like so. Okay. And so that means that x is equal to, I'm going to use implicit differentiation now, the hyperbolic cosecant of y. Right? And so now if I differentiate both sides with respect to x, I'll have 1 is equal to minus hyperbolic cosecant of y, hyperbolic cotangent of y, times the derivative of y with respect to x by implicit differentiation. And now all I'll do is solve for dy over dx. So we have dy over dx is equal to -1 over CSCH of y times the hyperbolic cotangent of y. Okay. Now we know from a trigonometric identity that you're going to prove, we know that the hyperbolic cotangent of y is equal to plus or minus the hyperbolic cosecant squared of y plus 1. Okay, so it's a multi-valued function, which, okay, now we know that the hyperbolic cosecant squared of y is equal to x, right, from here. So this is equal to plus or minus the square root of x squared plus 1. All right, so if x is greater than 0, then the hyperbolic cotangent of y is greater than 0. Okay, and so you can demonstrate that by graphing it, looking at the graph of the inverse hyperbolic cotangent function. And so that being the case, then the hyperbolic cotangent of y is equal to the plus part. Okay, x squared minus 1. Okay, and if x is less than 0, okay, then the hyperbolic cotangent y is less than 0, and so the hyperbolic cotangent of y would equal to the negative of x squared, the square root of x squared minus 1. Okay, so in either case, we would have the derivative of y with respect to x would equal to -1 over sheesh of y times the cof of y. Okay, and then we just replace those with their representations in x. And since the output should always be negative, to keep x from altering the sign, we'll just take the absolute value of x. And we know the square root of x squared minus 1 is always positive for x for on the domain. Okay, so there we have it. You can finish reviewing the technical notes. The technical notes are essentially solutions to many of the problems in section 3.11. So that's all I'm going to do talk about for Section 3.11 hyperbolic functions. I went way beyond what the class requires, but since I have the luxury of doing videos, I can make them as long as necessary. Okay, so here's the deal. I certainly hope that you're nearing completion of your Chapter 3 WebAssign problems. I also hope that you've almost have your project for Chapter 3 completed. And so those are things that need to be done. And then since we're now finished with all the lecture notes on Chapter 3, that means that we need to take our Chapter 3 Part 2 test. So please consult with the schedule on the class website to know when your Chapter 3 Part 2 exam will be available. And as always, if you have any questions, see me during my office hour or shoot me an email, and we'll get all the unsettled issues resolved for you. Okay? So good luck and stay in touch, please.